In this class, we will continue our discussion of how hypotheses are tested in multiple regression. When we shift our focus from the model to individual predictors, we will test hypotheses concerning the partial regression coefficient, or B. Our research hypothesis concerning intimacy, or any other predictor in our model, is that it will make a significant unique contribution to the prediction of the variance in Y. Our null hypothesis will hold that the predictor fails to make a unique contribution to the prediction of Y in the population, or that B equals 0. This null will be tested using a t-test. As with any t-test, we will divide our statistic of interest, in this case B, by the standard error for that statistic, and in this case that is the standard error of B. Our degrees of freedom for this test will be equal to n-1 minus the number of predictors. Because there are multiple predictors in multiple regression, and we are testing the null hypothesis that B equals 0 for each predictor, the results are often displayed in statistical software programs in a table, much as the one pictured here in this slide. Note that there is a separate B and a separate t-test for each predictor. The B's in this example were used in the first class on multiple regression. Also, the constant for the equation is also listed in the table under B. Here it is 10.50. Note this example has an SIG column which reports the probability associated with the t-value, our test statistic. This column tells us the result of the test of the null hypothesis for each predictor. By looking at this column, we can quickly see which null hypotheses were rejected and which were retained. The probability for rejected null hypotheses will be less than alpha, or less than 0.05. Before going to the next slide, see if you can determine which null hypotheses were retained and which were rejected. Then consult your table to find the critical value that was used to test these hypotheses if n equals 100. We would reject the null hypothesis for the predictors intimacy and income, but we would fail to reject the null hypothesis for anxiety. Note that the t-values for intimacy and income exceed the critical value of t equal to 2.000, but the t for anxiety is less than the critical value. As discussed in previous slides, we would select the most conservative of the two critical values that fall on either side of the degrees of freedom for our set of data. Thus, degrees of freedom equals 60 offers us the most conservative of the two critical values. Also note that these findings are consistent with the SIG column, where the probability for the test statistic for intimacy and income are less than 0.05, and the probability for anxiety is greater than 0.05. Before going to the next slide, please answer the following question. How would you interpret the finding for the predictor intimacy? We would say that the null hypothesis that the predictor made no unique contribution to the prediction of variance in the criterion is rejected because the test statistic exceeded the critical value. We would conclude that intimacy uniquely predicts variance in life satisfaction scores when the contribution of all the other predictors in the model are simultaneously considered. I know this is a real mouthful, but remember the size of B depends on the other predictors in the model. As discussed in a previous class, the size of the area of Y uniquely predicted by a single predictor will change when other predictors are added or removed from the equation. We would also say that increases in intimacy predict increases in life satisfaction. This is based on the positive value of B for the predictor intimacy. If B had been negative, we would say that increases in the predictor predict decreases in the criterion. While big R cannot assume a negative value and doesn't describe direction, the partial regression coefficient can be positive or negative and will be determined by the direction of the bivariate correlation between the predictor and the criterion.